Okay, so let's return talking about anesthesia still. Although really this next section actually isn't just about anesthesia. It's really telling us about consciousness and the brain more broadly, and it does also even relate to sleep. Specifically trying to understand other neural markers of anesthesia, neural markers of sleep, and then broadly neural markers of the conscious brain in general. And to understand how this works, you have to kind of go into a domain of neuroscience called network neuroscience. And so network neuroscience is just looking at connections between nodes and areas. And so here, for example, this is a visualization of a certain network map. And I wonder if people recognize what it is. This is actually a network map of air travel across the greater United States. So this is, Seattle, San Francisco, Los Angeles, and maybe Chicago. I don't know, whatever. Maybe that's Chicago. I have no idea. It's irrelevant. Detroit, Cleveland, probably Cleveland. Why do I keep doing this? So here you can just see there's this link between all these different network hubs, where in these cases a hub is an airport. I've never watched Game of Thrones, but people who have watched it tell me that this is somewhat correct after a couple seasons, although they said that Jon and Daenerys should be connected because they're apparently thing. I don't know, but it's this idea of you can see that there are these characters and their relationships to one another. But specifically, we can do this when talking about networks in the brain, or we can not just look at the gross anatomy overall, but we can actually get an understanding of how different parts of the brain are connected to one another. But in this case, rather than using something like DTI, we can actually do what's called functional connectivity analyses, okay? So a functional connectivity analysis is just basically finding brain areas that fire and go quiet at the same time, okay? So for example here, what I'm gonna show you is the bold signal, so this is fMRI, in the left auditory cortex and the right auditory cortex, and this is over time, okay? So we're gonna just plot the rise and falls of the left and right auditory cortex over time. And it looks something like this. Now, what do we notice? We notice that they are highly correlated, that whenever the green rises, the orange rises. Whenever the orange falls, the green falls, okay? Now we're looking at left auditory cortex and left visual cortex, okay? And now they're very uncorrelated with one another. There's actually almost basically no correlation with them. Now, why would that be, okay? Why would it be that you would have a correlation between these two brain areas and not these two? It's pretty simple. Whenever you hear something, usually both your left and right auditory cortices are going to get activated by that signal. However, you could hear something but not see anything different whatsoever. You could close your eyes and your auditory cortex could be doing lots of things while your visual cortex is basically going silent. So what we're going to do is we're going to look at these correlations between different brain areas, okay, which we refer to as functional connectivity. They're connected by their functional profile in light of drugs, for example, like propofol. So this is going to give us a capability of looking at network neuroscience of anesthesia. And effectively what you find is that the awake brain is much more connected than the propofol brain. So PILOC stands for propofol-induced loss of consciousness, okay? And so what you can do is you can just measure the functional connectivity between different parts of the brain at both a local and a global scale. Local just means nodes that are right next to each other, close in the brain, and then global means, nodes that are very far apart. And what you can actually just see is that both long-range connections and short-range connections, ones that are close, ones that are far, vary as a function of wakefulness and propofol loss-induced consciousness. When you're awake, both your long-range and your short-range connections are more functionally connected than when you are anesthetized. So you can just basically see that your brain is losing a little bit of its coherence, both at a macro global scale and at a local scale. And so this is thought to be another neural signature of both anesthesia and consciousness, where it's like, oh, your brain is not connected as much to itself when you are unconscious versus when you are conscious. So this is true in anesthesia, but if we want to talk about this as a potential marker of consciousness in general, it's natural to wonder about another state of consciousness, but for example, sleep. And it actually turns out that it's the same idea as with anesthesia, this sort of loss of connectivity. And you could see it with fMRI, but there's actually also other ways that you can do it, which I like quite a bit and I think are more compelling. One of them comes from TMS. But specifically studies where you do a combination of TMS and EEG while you're asleep. So I've also done studies like this. You go into a sleep lab, you get outfitted with a blue cap, and then they also put the TMS little magnets on top of you, and they will stimulate your brain while you are sleeping. And they do it just a little bit. It's not so much that it would, for example, wake you up. And here, what you can just see is by having a combination of both TMS and EEG, you can not only be measuring the activation across the scalp, but you can then deliver pulses and see what happens to those pulses that you deliver to the brain when you're awake versus when you're asleep. Okay, so now what we're going to do is we're going to see what happens when you introduce some activity into the brain through TMS while the patient, in this case, is awake. So this is a person who's totally awake. We're going to zap their brain here, and we're going to see how the activation propagates across their cortex when they're awake. And then in a second, we'll compare it to when they're asleep. So let's check this out. So you TMS, and as you'll see after a couple of seconds, you'll start to notice that this yellow and red blob, an orange blob, starts to kind of move around the brain. It goes to the left hemisphere, it goes to the right hemisphere. You can see it in the left frontal lobe, the right occipital lobe. It's bouncing around the brain, okay? And actually what you can do is you can kind of take snapshots of it, and you can see, okay, if this O ring is where we did the initial TMS, that's why it's, 15 milliseconds later, the activity is still right there. You can see it goes a little bit further back in the head. It goes to the front of the brain. It's bouncing around basically, okay? The idea being that your brain is so interconnected while you're awake that if you just deliver some information into it, it's gonna just bounce around like a ping pong ball, okay? Now let's see what happens when you do the same experiment, except now the patient is asleep, okay? So let's do the same TMS of the same person, except now this person is asleep. Let's see what the activity does there. Notice how that yellow and orange blob basically stays right at the arrow. It doesn't really go anywhere, okay? It doesn't bounce around. It doesn't go to the frontal lobe. It doesn't really cross to the other hemisphere as much. It doesn't go to the occipital lobe or anything like that, okay? When we look at this same plot here, we can see that the oval and the ring and the little cross stay on top of each other. Again, the idea is that when you're asleep, your brain is not as interconnected. So when information gets in one location, there's not enough highway systems now connecting one part of the brain to the other for that information to go to the frontal lobe, the occipital lobe, the parietal lobe, and so on and so forth. So this global connectivity doesn't seem like it's allowing the information to propagate when you're asleep in the same way that it was while you're awake. There is not, as far as I know, data that has been done to do this with anesthesia, but I've heard of groups that are doing the same thing right now with anesthesia. And I would bet, good money that you would see pretty anesthesia to see similarities and differences. Oh yeah, that you'd see pretty much the same similarity and differences in terms of sleep and awake for anesthesia and EEG or anesthesia and TMS rather than EEG and TMS. And so this is a possible kind of candidate signature of unconsciousness in the brain in general, that information doesn't get integrated at a global scale across the cortex where it's not interconnected with one another, and that this global integration is itself a signature of consciousness in the brain in general. Your brain has to be massively integrated and connected and talking to itself to differentiate between when you're anesthetized and when you're awake versus when you're asleep and when you're awake. But to just give you one last, and we'll end this unit on this section, more evidence of this idea of interconnection is actually scientists have recently discovered that you can effectively turn consciousness on and off via this brain structure called the claustrum, which is important because it's at like the center of a hub that connects all these different parts of the brains to itself. So when you look at the claustrum here, which is in blue, it's this little sliver there. It doesn't look that impressive from this angle. But when you look at it from the side, you can see like, oh, okay, I get it. It's part of the thalamus. So it's part of this brain structure that is connecting all these different parts of the brain to one another. It's a subset of the thalamus that is making it something like what we've talked about before, Grand Central Station, so that information can pass through it to get all these different other parts of the brain. And it just so happened that there was a patient who was having problems with epilepsy, and so they put a bunch of electrodes in her brain to kind of map out her epileptic seizures. And it just so happened that one of those electrodes went right next to the claustrum so they could stimulate the claustrum. And so now I will read to you what happens. I don't have any videos, unfortunately, but there's some quotes I can read to you of describing what the physicians experienced when they stimulated this patient's claustrum. So when they were stimulating that particular electrode I just showed you, so this electrode here, we're going to call it A14. So stimulating 14 resulted in immediate impairment of consciousness in 10 out of 10 times with arrest of reading, onset of blank staring, unresponsiveness to auditory or visual commands, and slowing of spontaneous respiratory movements. The patient returned to baseline as soon as the stimulation stopped with zero recollection of the events during the stimulation period. Occasionally, the induced impairment of consciousness was associated with scanty, preservative, and incomprehensible verbal output consisting of one or two syllables with a confused look on the face. So basically, I'm going to raise my finger. Everyone look at me. I'm going to raise my finger when the claustrum is getting stimulated. But what happened is you would have a patient who would be talking like normal, and then as soon as you turned the claustrum off, they would kind of, and then they would kind of freeze like that. And then when the stimulation goes away, they would come back online. And it's basically just like a little on-off switch. And why is this happening? The idea is that when you stimulate this little area there, you're basically injecting a lot of noise. You're injecting some traffic jams into the claustrum that's basically getting in the way of all the signals that would normally be flowing through the claustrum. And so basically you're preventing, through this electrical stimulation, information from freely flowing across the cortex. And when you prevent the information from freely flowing across the cortex, that's when you're going to get issues like impairment of consciousness, inability to speak, lack of memory, and so on and so forth, because of this idea that global broadcasting is a potential signature of conscious processing. Okay, so when we come back, we'll talk about one last thing, so our last unit, which will actually be talking about disorders of consciousness in general, but with a specific focus on the vegetative state and what differentiates a vegetative state from a non-vegetative state, and are there ways that we in fact can tell, are there people who might be unable to move or respond or seem like they're unaware, but in fact can we use neuroscience methods to determine that they in fact are aware? Hint, hint, the answer is yes. So come back and I'll tell you all about that.